Assalamualaikum and a very good day, everyone. First of all, my name is Nurshafinaz. I'm from MJIT UTM. Today, I will be presenting my research paper entitled Regimes of Flow-Induced Vibrations and Wind Energy Harvesting Associated with Cylinder Plate Configuration. So this paper is an output of collaborative work between myself, Associate Professor Dr. Muhammad Shukri, Associate Professor Dr. Sheikh Ahmad Zaki, also from MJIT UTM, and Dr. Izwan Amin Ishaq from UTHM. I believe all of us are aware of the increased utilizations of small electronic devices in our daily life. These devices used to be some kind of luxury, which has turned to be an essential item for us to go through our daily life. The nearest and remarkable example is our handphones and gadgets. This increasing demand of small electronic devices has encouraged new alternative of power supply, particularly for remote application such as wireless sensor nodes for structural health monitoring. Besides, we can also expect the alternative power supply should come from resources that could produce abundant supply, which to ensure the continuous and smooth workflow. It is also can be expected that with the rising applications of small electronic devices, the problem with waste management of conventional finite lifespan batteries, which are our normal battery, would be linearly increased and daunting. And therefore, the interest of exploring the renewable energy supply from ambient resources has increased remarkably by means of numerical simulations and also by experimental measurement. Harvesting the energy from renewable resources is commendable, and as a part of functioning member of society, I personally would recommend this approach. We do know that there are several known renewable resources, which includes the wind energy, water, solar, and also biomass. As for our subject of matter today, we would like to propose harvesting the energy from flow-induced vibration, which could be from wind or water resources, right? And due to its highly energetic wave and force components, hydro or water resources has gained the popularity as an ideal flow energy harvester among researchers. Okay, so this is the undeniable fact. However, for the wind resources, the potential is still underexplored. This is might be due to its self-limiting and inconsistency of character. So what is actually flow-induced vibration? By definition, flow-induced vibration is actually a motion induced on a body by the unstable force at the near wake due to the formations of vortex shading. It happens when the frequency of flow is equal to one of the body's frequency. Alright, so the vortex shading, or known as von Karman street, was developed from the fluctuating force due to the flow separation when the fluid flow past the body, as you can see in the diagram from my slide. Alright, so previously we have acknowledged the drawback of wind energy or wind resources. Alright, so how to overcome the self-limiting and also the inconsistency character of wind resources is by suggesting a control strategy approach. Okay, so according to Choi et al., there are two flow control strategies. All right, so the first strategy is called boundary layer control. So the first strategy is by controlling the boundary layer of the bluff body. However, this method is only applicable to a bluff body with a curvature and has no fixed separation point. For example, a circular cylinder into the form a circle. All right. So Chang et al. Has introduced a roughness strip which is embedded on the circular cylinder to expedite the vortex generation and maintains the increasing amplitude of vibration. This method was also applied by Bernitsas et al. For the Vivas vortex generator, and also Ding et al. By numbers of numerical simulation. The second method, which is a more general approach or control strategy, is by directly control the wake of a bluff body, and usually by placing some kind of geometry in the wake of a bluff body. So this method is applicable to all bluff body. And for example, the water harvester, the energy harvester, uh, the hydro energy harvester studied by Coede et al. Has suggested a strip plate downstream to the cylinder to expand the working velocity of non-uniform river flow. Okay, so as the bluff body opted in our study is a square cylinder, the suitable or more suitable control strategy to be used is the direct wake control. Based on previous studies, the effectiveness of this type of control is highly dependent on the gap separations or the locations of control between the main bluff body and the control body. All right. Now we have come to the methodology that was opted in this study. So this study is a numerical oriented by using CFD software OpenForm. In this study, the influence of flat plate in controlling the wake of a square cylinder is investigated by designing the locations of flat plate downstream to the cylinder. The first case that we investigated was the case of 0.1, of which the plate is located nearest but not attached to the square cylinder. So we took 0.1 to emphasize that that is the closest of location for the flat plate to influence the motions of or the flow induced vibration experienced by the square cylinder. And then we expand the location or the gap separation between the square cylinder and the flat plate from 0.5 to 3. All right. So all these parameters which was computed into our CFD software are corresponding to the previous experimental measurement by Maruai et al. Okay, so as you can see in the diagram, in the slot of computational domain, so the figure presents the schematic diagram of computational domain and the boundary conditions. The mesh surrounding to the square cylinder is created in block mesh utility from the dictionary file block mesh in the OpenForm system, and the motions of moving mesh is resolved by point position update based on the Laplacian smoothing equation. The automatic mesh motion algorithm developed by Jasok Tukovic was adapted in this study. Alright, so the CFD technique opted in this study is finite volume method FVM, and as you can see in the table in this slide, so all the discretization and also the numerical method was included, and then the flow solutions are obtained, okay, by solving the Reynolds average Navier-Stokes equation. And the turbulence model, which was exploited in this study to solve the Reynolds stress equation, was the turbulence model of SST K omega. And the pressure velocity coupling algorithm used in this study is the merge pimple for transient flow. Okay, and then moving on to the estimations of potential harvested power. So basically the harvested power equation was first introduced by Bernitsas et al. And with the hypothesis or uh, the the hypothesis that the flow-induced vibration is practically modeled as a single degree freedom of elastic system. So basically the power equation was derived from the second order of equations of motion, and in order to measure the efficiency of cylinder plate configuration, the harvested power was divided by the power of fluid from the incoming flow. So that is how we estimate the potential harvested power in our numerical simulation. So the first result is for the close proximity case when the gap separation between the cylinder and plate is 0.1. It is quite important to mention that for a single isolated square cylinder of similar computed parameters, the coexistence of VIV and galloping was observed. So this was reported by previous study by Maruai et al. So therefore, in order to discuss the influence of flat plate at different gap separation, this reference would be incorporated later on and also for this case. Now, based on these figures, we can see that both vibration and lift force coefficient have shown an increment trend or increasing trend with the increments of reduced velocity. The resulted high amplitude vibration was also confirmed to be due to the vortex shading influence in the wake with the coincided corresponding frequencies of both vibration and also the lift force data. This was further confirmed through the phase lag analysis and the flow visualization. And based on the flow visualization, as you can see from my slide, the 2P and 2S vortex pattern was found during the reduced velocity of 18 in the wake of cylinder, which occurs and translated when the bluff body experiences high vibrational amplitude. This is based on previous study by Williamson and also Roshko. All right. Right, for regular cases of which when the gap separations is between 0.5 up until 3, so basically based on the dynamic responses presented in the 4 figures in the slide, we can conclude that there are 3 regimes of flow-induced vibrations were discovered. Okay, so the first and second regime shows the pure VIV character based on the coincided trend of frequency, vibration and frequency of vortex shading, and this shows that the influence of flat plate in controlling the wake of square cylinder is still very much relevant up until gap separations of 2D. And also the log-in of VIV was observed at reduced velocity ranging between 8 to 11 for regime 1. And for the second regime, there was an intermittent transitions of character was found for reduced velocity 11 and 12 based on the lift force coefficient trend. However, as the velocity is further increased, the trend is recovered back like the ones in regime 1. So regime 1 and regime 2 are similar to the pre-formations regime defined by the Unell and Rockwell, which the formations of vortex shading is delayed and completed only downstream the plate, which means which showcase the influence of flat plate in controlling the wake of our square cylinder. And this can be observed by the flow visualization in the slide. In the lower branch of velocity and galloping towards the higher branch of velocity was appearance and observed for regime 3. This is reflected and similar to the isolated case based on previous study. From this, we can conclude that the influence of flat plate towards the flow-induced vibrations experienced by the square cylinder in this regime, regime 3, starting from when the plate is located at gap separations of 2.5D, is declining and diminished. Alright, so the declining influence of flat plate can be further confirmed by the completions of vortex shedding formation in the wake of cylinder, as you can see in the flow visualization. Okay, based on the comparison of these three remarkable potential, cylinder plate of configuration with gap separation 0.1 proceeded as the most optimum configuration. Okay, so this configuration reflects on the high efficiency rating without compromising the size of the end product for the harvester, because where we have a small gap separation, meaning that our harvester to be expected not very large, okay, as compared if we have a bigger gap separation between our square cylinder and also our flat plate. With that, thank you very much for your time, attention, and participations. I really do hope these findings could benefit us all directly and indirectly, and I wish that this potential of wind energy harvesting could be further explored in nearest future. Thank you very much. Assalamualaikum.